Yeah. Okay, let's begin. So today we're very happy to have Geoff Pennington. He did his PhD at Stanford University and then afterwards joined UC Berkeley as an assistant professor in 2020. Geoff works at the interface of quantum information, quantum computing, and quantum gravity, and has done, among other things, some real important work on the black hole information problem. So we're really happy to have him here to tell us about what do black holes actually get up to when they're left on their own. Thanks.
Okay, so thanks very much indeed for inviting me to come talk. So this talk is going to be mainly about a paper that's in theory coming out on archive this week. It's been coming out on this archive this week for a little while now, but that tends to happen. It's work with Adam Brown, Luke Eliescu, and Misha Ishachuk. In particular, Misha he's now a postdoc. He was a grad student when this started. In fact, this project was meant to be done in time for his postdoc applications. It's going to end up being closer to his second postdoc applications than his first, but but he not only did sort of almost all of the deep technical calculations, but also worked out a lot of the physics. So I really want to highlight his contribution. So what's the talk about? Can I make that disappear? Okay, so it's about possibly, this is the black hole initiative, and it's about possibly the most basic question you could ask about a black hole, which is take a black hole on its own in the universe, what happens next? This is gone.
Just click on the slide.
So by a universe, I mean a universe that looks like ours in the sense that it's described by Einstein gravity, general relativity, plus the Standard Model. It's not going to be like ours in the sense that our universe is cosmological. It has dark energy, dark matter, it's expanding. There's all sorts of physics going on there that I'm not going to worry about. I'm just going to consider a universe with the Standard Model plus gravity with zero cosmos. Furthermore, we're not going to be interested in sort of subtle questions about what happens to this black hole, like is information lost? Is it secretly preserved, but it's very hard to tell? Anything like that. We're going to be interested in the most basic questions you could ask, like what sort of particles get emitted, what will their energies be, things like that. However, it's going to turn out that if we start with a generic, sufficiently large black hole, and sufficiently is carrying a fair bit of weight here, it really needs to be very, very big. Then even just answering those basic questions will require a full-fledged calculations in strongly coupled quantum gravity. In particular, Hawking-style calculations, so the famous original derivation of Hawking radiation from a black hole, treated the sort of gravity as completely classical and then just considered fluctuations about that fixed background. And those sort of calculations will give completely wrong answers almost all of the time around the evaporation rate. So I actually want to make a strong claim that people should feel free to call me out on, because it may be totally wrong. I want to claim that this is going to be the first example of a controlled calculation in the Standard Model plus gravity of Lorentzian dynamics where there are really large fluctuations in the metric, large quantum fluctuations in space-time geometry, but we're still able to keep them in control.
So by almost always wrong, you mean
almost all of the evaporation.
but if you
by time.
like the average energy flux or something.
Even the average energy flux for almost all of the evaporation, it will give completely the wrong answer. We'll get that. If you still have that question near the end, then ask me again. Okay, great. But before we get to anything fancy like that, let's just start with classical general relativity, which should be more familiar to most people in this audience than some of the quantum stuff. So in classical GR, there's this thing, the no-hat theorem, that was understood, at least at a physics level, by the early 1970s, which is that if you have any black hole and you wait for a little while, it will settle down to an equilibrium solution. And that equilibrium solution is uniquely characterized by its mass, its charge, its angular momentum. Okay.
You'll be in 4 dimensions.
4 dimensions all of the time. Yep. Otherwise, there are all sorts of qualifications here. It's also worth noting that to a mathematician, the fact that it settles down to equilibrium is still something of an open question. It's known. There are some very technical proofs that show it in if you start close enough to a pure black hole and so on. So generically, you get what's called a Kerr-Newman black hole, where you have a charge that is scales order the mass of the black hole, and you have an angular momentum that scales order the mass. Again, in classical general relativity, after this, nothing will ever happen. Again, there's minor qualifications. You may have super radiance or something, but eventually you'll settle down to some stable classical black hole, and it will just sit there for eternity. Of course, even in 1972 or whatever it was, when this story was pretty worked out, everyone would have said that there have to be some sort of quantum corrections to this because everything in our universe is quantum mechanical, and so everything is corrected. But probably qualitatively, nothing really changes. These corrections should be very tiny. These are very classical large objects. So basically, this story should stay the same. In 1974, though, Hawking went ahead and calculated those tiny quantum corrections and found something very, very interesting. So how did he do that? Well, we didn't understand. We didn't have some complete theory of quantum gravity. We still don't. But that's okay, because for a large black hole, the space-time should look very classical. So what Hawking did is what I said a few slides ago. He just treated the space-time as a completely classical object, and then he treated the fields within that space-time, so the electromagnetic fields, graviton fluctuations, and in general, all the particles in the Standard Model each have their own quantum field, and he treated those fields fully quantum mechanical. So this is called doing semi-classical gravity. And what he found was, of course, Hawking radiation. So the first thing he found that really should have been noticed before then, and shouldn't have had to be noticed in the context of black holes, because really it has nothing to do with black holes, that if you look at quantum fields very close to the horizon, then the different quantum fields will be entangled with each other. In particular, fields just outside the horizon will be entangled with fields just inside the horizon. This has nothing to do with horizons. This just has to do with how quantum fields work. Any state of quantum fields will always be entangled, meaning that you can't talk about the state of the field at just one point. You can only talk about the collective state of the field at all points. It's not defined on its own. In particular, if you just look at the fields outside the horizon on their own, or outside any other surface, then they will look thermal to an observer who's accelerating really fast and so remaining just outside the horizon. Again, this has nothing to do with gravity. It's present in completely flat space, Minkowski space as well. It's called the Unruh effect. It, again, really should have been thought about before the Hawking effect, but historically it wasn't. It was Hawking who sort of discovered this as an intermediate step in his calculation. But the interesting thing from a black hole point of view is that the black hole dynamics allow the fields outside the horizon to escape off to infinity, as I showed there, whereas the fields inside the horizon, by definition, are trapped inside forever and can never escape. And so it takes this very short-range entanglement with stuff that sort of looks noisy, looks thermal if you sort of accelerating, and turns it into long-range entanglement stretched across the universe, where these modes at infinity are now actual thermal modes that even just some free-falling observer will see. And I've written here the formula that Hawking found for the temperature of the black hole. And I really want to emphasize what an amazing achievement this formula is, because it's like the first, Netta's laughing because she's heard me give this joke at least 20 times. What can I say? I never find it gets old. It's really the first calculation in gravity that brought together sort of all the different, so it's the first calculation that brought together all the different major subfields in physics in one calculation. You can see that just looking at the formula. We have a Planck's constant in there, an h bar, so this is inherently a fundamentally quantum phenomenon. It's c cubed, so it's relativistic, involves speed of light, has gravity involved, has Boltzmann's constant involved, it has thermodynamics, and of course it has pi, so it has circles. Okay, so we have thermal radiation coming out from this black hole at some temperature, so that thermal radiation is carrying energy. Conservation of energy then means the black hole must be losing mass over time. then you can actually calculate and show there's in fact a negative energy flux heading across the horizon. So that's why I think. But this never stops. This is a very slow, small process, but it keeps happening, it keeps happening, it keeps happening. And so over time, black holes evaporate. Quantum black holes are just fundamentally different objects. The classical ones, they're not stable. Okay, great. So that tells us that this mass of the black hole actually gets smaller over time. What about the two other properties characterizing it? Well, let's first consider the angular momentum. So the Hawking photons that get emitted can carry angular momentum. They generally will have pretty small angular momentum, but they can have 0, 1, or 2 quanta of angular momentum. And if I have a black hole that has a large angular momentum, like a Kerr or Kerr-Newman black hole, then the Hawking quanta will tend to carry angular momentum in the same direction as the black hole. You can just do the calculation and see this. Okay, great. You can then do another calculation that's a bit more technical, but it just works out. And you can show that if the field's present in your theory of the standard model, then the black hole will tend to lose angular momentum faster than it loses, that should say loses mass rather than loses charge. I apologize. So if you start with an angular momentum that's of order the mass squared, then you'll lose most of the angular momentum while still having most of the mass, and you end up with something that looks like a Schwarzschild-Rosen-Austrian black hole. You'll get to some pretty small angular momentum. Okay, so angular momentum is not very interesting. It's all going to radiate away. It's going to play no further role in this talk. I'm going to assume from now on we have basically 0 angular momentum. Okay, the more interesting one is charge. And the reason that's more interesting is that all the charged particles in our universe are massive. There are no massless charged particles in our universe. So unlike angular momentum, which can be carried away by photons or gravitons, the charge of the black hole needs to be carried away by massive particles. And at low temperatures, as the black hole gets big, it gets very low temperature. At low temperatures, it's very hard to create a massive particle. So you would expect that Hawking radiation of these charged particles would be exponentially suppressed for large black holes. And that's true if the black holes aren't charged. But charged black holes can still be produced even at 0 temperature in the presence of a strong enough electric field. This is a phenomenon called the Schwinger effect. It's another phenomenon in quantum field theory. It's already understood in this case back in the 1950s. So the horizon electric field of a black hole is just given by Newtonian-like formula. It's roughly the charge over the horizon squared. Horizon radius, roughly the mass. So it's roughly the charge over the mass squared. So as the mass gets smaller, this electric field gets stronger. Eventually, if it becomes strong enough, we'll start emitting either electrons or positrons, depending on the charge of the black hole. The black hole will be able to discharge.
Is this an external electric field?
This is just the black hole. If the black hole carries charge, the charge of the black hole will create an electric field, and that will create Schwinger effect. Okay, so that's how the black hole can lose charge. And we've now explained how the black hole can lose mass, charge, and angular momentum. So by 1980, all of that was pretty well understood. And we seem to have good semi-classical calculations that will tell you what happens to an evaporating black hole all the way down to sort of the last tiny second of its life, where it gets really, really tiny. Its size becomes the Planck scale. Its temperature becomes the Planck temperature. Quantum gravity clearly comes into play and everything breaks down. But, you know, that's just a tiny, it's the 0.000%, 1% of the evaporation. We don't really worry too much about that. Of course, there were other weird things about these calculations that were after we'll start the talk. In particular, they seem to suggest that information that fell into the black hole was lost from the universe forever. So we threw something in, this radiation coming out, just involved physics of the horizon. This thing quickly falls across the horizon. So it doesn't seem like the system cares about the state of the stuff we threw in. And that's in contradiction with the normal rules of both classical and quantum physics, where in particular in quantum mechanics, you have unitarity, which says the same information is always present at all times. So this became one of the sort of big dominant problems in quantum gravity. We had these seemingly very solid calculations that looked totally legit, but they were giving this weird answer. So it's really only in 2019 that we understood how to do a calculation in quantum gravity or semi-classical gravity that showed that actually the information did come out after all, and everything was consistent with quantum mechanics. That's a very cool and interesting story. Obviously, I was very involved in it, and I think it was great. I'm biased towards it, as is Netta, who was also heavily involved. But the upshot is that for simple observables, if you're just interested in things like the energy spectrum with the radiation coming out and so on, then the semi-classical Hawking calculation is still the right calculation to do, and it doesn't go wrong in any way. Only when you consider particularly very complex, in fact, exponentially complex observables, very subtle features that diagnose whether information is really being lost, that you get these large quantum corrections from quantum mechanical effect called spacetime work. That sounds very cool and is very cool, but I'm not going to explain anymore. And when you include those effects, you get something consistent with quantum mechanics. But that's not the topic of this talk. So I'm going to move on to a much more simpler way, in which less subtle way in many ways that the semi-classical calculation is breaking down. And that's because of a very simple feature of black holes that I'm sure everyone is familiar with, which is that there's a fundamental bound on the mass of the black hole in terms of its charge and its angular momentum. This is the extremality bound. It says that the mass of the black hole has to be at least as big as the square root of the charge squared plus the angular momentum of the mass squared. You try to mathematically write down a solution that violates this bound, you don't get a black hole, you just get a naked singularity. Okay, so the key point is that if we start with a big enough initial charge, then even when we approach this bound, so the charge, say angular momentum is 0, so the mass approaches the charge, then the electric field at the horizon is going to look like the charge divided by the horizon radius squared. So that's roughly the charge of the mass squared, which is 1 over the charge of the black hole. So if the charge gets really big, this electric field starts to get really quite small, even if your black hole is as strongly charged as it's possible to be. If it's big enough, then this is too small an electric field to have a Schwinger effect, and the emission of charged particles becomes exponentially slow. You still in principle have the Schwinger effect happening, but it's exponentially suppressed in the electric field divided by this critical electric field. Turns out the required charge for this to be true is very, very big. Roughly, this is because an electron or a positron is very, very light in Planck units, and it has charge 1, or well, it has charge 1 over 136, 1 over 137 in Planck units. So the required charge needs to be really big. So the electric field in Planck units required for Schwinger pair production is actually very small, even though it's far stronger than any electric field we've ever made in history. But if you have a big enough charge, bigger than about 10 to the 44 times the charge of the electron, then this will be true. So is this realistic for actual black holes? Well, there are black holes in our universe that have sufficient mass that if they were highly charged, if they were sort of near extremal, they would be well above this bound. In particular, the black hole Sagittarius A star at the center of our galaxy has more than enough mass to accommodate this charge. The problem, of course, is that there's all this charged matter around it. Any large black hole will tend to absorb matter with the opposite charge from its charge, and so it remains very, very close to neutrality. There's some actual practical bound on the charge as a fraction of the mass that's far, far smaller than the extremality bound. Black holes in our universe are very, very close to neutral. So all of this physics is not going to be relevant for real life black holes. Also not going to be relevant because we're going to be getting some really long timescales showing up soon that are going to be far longer than the age of the universe. In fact, even just Hawking radiation from realistic black holes is already much longer than the age of the universe, and we're going to get much longer than that. So, you know, there's a certain point where it's in for a penny, in for a pound in terms of is this experimentally relevant? But I think it's still fundamentally interesting as a basic question about what happens.
You need to say what the mass is to get that 44 in there. Where does that number come?
Yeah, sorry, the 10 to the 44. It's basically the mass 1 over the mass squared of the electron in Planck units. That's where the known. You've got to suppress Schwinger pair production of the electron. The electron is very light in Planck units, so it needs a very small electric field in Planck units to have it be suppressed. Yeah. Okay. You still seem a bit unhappy.
No, well, I'm trying to do the calculation.
Yeah. Yeah.
Annoying for a second.
Yes.
So you say the solution is going to have a naked singularity if it's super extremal, of course.
Yes.
But excluding naked singularities is a little bit complicated in this talk because you have an evaporating black hole. So there's going to be a naked singularity no matter what you do.
No, well, there's going to be.
The end state of evaporation is always going to be a naked singularity. So, in what sense? I mean, I'm just being annoying, but in what sense would you say this naked
I think there's a
singularity
difference
works?
between a naked singularity and quantum effects coming into play. Now, of course, you could have quantum states, which correspond to the classically have a mass that a charge greater than the mass. In fact, we do, and an electron is a good example. But I would say they aren't black holes, and there's no reason to believe that the number of them is given by Bekenstein-Hawking formula or anything like that. Okay, great. So let's just ask the question: what happens if we start with a black hole with a really big charge, say 10 to the 47, 10 to the 48, and we just leave it there? So it will lose mass, and it will lose angular momentum through Hawking radiation. So it will become a Rising-Nordstrom black hole. But it won't lose charge. So its mass will get smaller and smaller. As its mass gets closer and closer to the extremality bound, it turns out the temperature of the black hole will get smaller and smaller, will go to 0. But the way it does so is given by this formula. It scales in particular like the square root of, always forget to correct this, that should be the mass minus the charge rather than the charge minus the mass. There's a factor of I missing there. But it scales as the square root of the mass above extremality. Okay. So the interesting thing is when the mass above extremality becomes sufficiently small, in fact, it needs to be roughly 1 over the charge cubed, then this temperature becomes larger than the mass of the black hole above extremality. Okay. So in general, a thermal Hawking quantum emitted by a black hole, a single particle, will carry an energy that's roughly equal to its temperature. And so the energy that it's carrying off is far larger than the energy of the black hole above extremality, the sort of energy available for the black hole to give out. So this is a clear signature that the semi-classical approximation is breaking down, because the whole point of the semi-classical approximation is the classical geometry of spacetime isn't changing, yet there's one particle being emitted is ending up with something completely inconsistent with our original classical geometry.
But what's the mass of the black hole? Is it like, did you say? It was
Oh,
like Sagittarius?
Yeah, Sagittarius star. Yeah.
Is that a weird coincidence?
Yeah. I don't have any deep reason why. Yeah. I'd like to, yeah. I don't think there's any connection between Sagittarius star and 1 over the electron mass squared in Planck units, but I don't, yeah. It'd be interesting if there was. Yeah. Okay. So something's going wrong with our approximation. We're going to need a better description of what's going on. And this was pointed out in various papers, originally by John Preskill and various authors, including Frank Wilczek, then by Juan. And I think, were you on that paper, Andy? I can't remember if you were or not.
Yeah, I think so.
I think you were, right? Yeah. Also, Don Page wrote a nice paper about it. Yeah, this was some well-known problem, but it was certainly fair to say I think it was much less popular than the information problem. And basically the reason why is that for the information problem, it seemed like our calculation was super solid and there was no obvious reason why it wasn't the right thing to do. It just gave weird answers. In this case, the semi-classical calculation just obviously isn't self-consistent. It just sort of seemed like we needed a complete theory of quantum gravity to be able to make any progress. So, yeah, we didn't. So it seemed like, okay, wait around, either just sort of wildly speculate about what happens or wait around until we solve quantum gravity.
So.
Yep.
I think I got the whole point, but
Yep.
The whole story is coming because we have massless neutral particles like
Yes.
photons,
But no mass.
but our universe does not
Yes.
have massless charged particles.
Yes.
If they were present,
If they're present, the small
problem.
window, nothing interesting. happens.
and here you're assuming that the lightest charged particle is the
It's the
electron.
electron. Yes.
Thank you.
I think that's a pretty safe assumption.
No, no,
I
no,
don't
that's
think
fine.
there can be
That's
a
what
hidden
it is.
charged particle.
Yeah,
Yeah, exactly.
Yeah.
But yes, absolutely great. Okay. Great. So there's another way that you can see that the semi-classical approximation might be breaking down, even without talking about like becoming super extremal. And that's that near extremal black holes have what's called a very long throat. I think this should be vaguely familiar, at least to people. But roughly what happens is that you have some region where the space-time looks roughly like flat space, but then you have this long distance between the outer horizon of the black hole and there, where the size of the transverse sphere is roughly constant, and the radial direction and time look like what's called two-dimensional antithesis space. As we take the temperature of the black hole, go to zero, as we approach an extremal black hole, the length of that throat diverges, it becomes infinite. And as a result, tiny little changes in energy at infinity, the space-time geometry will completely change the length of the throat. They'll have some huge effect on the geometry of the throat. So that's a sign when you have sort of two solutions where you only change the boundary condition very slightly, but the geometry is changing a lot. That's the sign that you have some very light modes in your problem. You have modes, you have solutions that are, you have geometries that aren't actually solutions, but they're very, very close to being solutions, even though they're not. They almost solve the equations of motion despite not being close to a solution.
Excuse me, but I mean,
Yep.
you only get, I mean, in what sense does this go to infinity? Only if you try to go to the bifurcations.
Yeah, I'm talking about the full space-time geometries of the geometry of the bifurcation. I'm not talking about like falling along like affine ray towards the.
But somehow, okay, but the natural thing to do is to transverse, or like to intersect transversely the event horizon.
It depends what question you're interested in. This will turn out to be, yeah, the length of this throat becoming long. Like, okay, yeah, it will turn out for the problems we're interested in that this distance to the bifurcation surface is actually diagnosing something. Now, it's diagnosing the fact that the full rising Nordstrom space-time has what's called almost zero modes. So perturbative fluctuations about your classical solutions to the equations of motion that lead to a very small change in the action. Okay, and that's going to be
Maybe a dumb question, but.
Yeah.
As the temperature goes to zero and the length of the throat diverges, is the temperature uniformly going to zero, or is there?
is the temperature sort of fluctuating in some way? I mean, in some sense,
should
that's
we
what I'm
think
going to
about the
be
temperature?
explaining.
Okay.
Semi-classically, there's just the geometry is classical, and there's just some temperature that's smoothly going down. Yeah, what we're going to see is there's going to be big quantum effects, and all of that's going to change. Okay. Okay. So yeah, as I say, the presence of this long throat is related to having what's called these almost zero modes about the classical geometry. And in turn, that means that we expect there to be large, strongly coupled quantum fluctuations. The interesting thing is that the set of modes that become very light, that become these almost zero modes, have a very nice, simple, effective description. We can just, if you freeze out all the other modes that aren't super light and just talk about these ones, then we can describe them in terms of a two-dimensional theory that's called a certain theory called JT gravity coupled to SU2 gauge theory. It turns out in the last 10 years, it's been shown that that theory is actually completely solvable quantum mechanics. So we can treat those modes completely quantum mechanically and still be able to make progress, even though if we treated the whole space-time quantum mechanically, it would be a disaster zone and we'd have no idea what to do, it would all break down. So actually, so the reason this theory has been solved so much is that it turns out to be the same theory that describes a particular model in condensed matter physics, called the SYK model, at sufficiently low temperatures. It's like a good effective description of the SYK model at low temperatures. So this is an example of sort of universality in physics and quantum mechanics. It's this one theory that sort of shows up in a load of different. Okay, so the idea which goes back to a paper about 5 years ago by Luca Liesiu and Joaquim Turiachi, is to do a fully non-perturbative quantum treatment of two things. Firstly, the matter fields, which Hawking already treated that way. And secondly, these almost zero modes that are going to have large, strongly coupled fluctuations. And then we're still going to treat all the other space-time fluctuations semi-classically. We'll include sort of graviton fluctuations as quantum fields, but not large fluctuations. Okay, so as I say, this is not a new idea. It's about 5 years old, and it was done by Luca and Joaquim. And what they found is these effects lead to large changes of the thermodynamics of the black hole when you get to very low temperatures. So they considered a theory where you have no light matter fields at all, no photons or gravitons or anything. Or at least they ignored the gravitons. The gravitons have to exist. But what they showed is that when the mass above extremality gets much smaller than this, the scale where things seem to go wrong, where the temperature seems to get much larger than the mass above extremality, instead of being the temperature scaling as the square root, the mass above extremality, it scales linearly with the mass above extremality. So this seems much, much better, right? Because now if I have a photon carrying energy T, then it doesn't make the black hole super extremal anymore. But of course, thermal photons don't just have to have energy exactly T, they have some distribution that's exponential in e to the minus E over T. So in general, some small but order 1 fraction of time, they'll have energy greater than 3 over 2T. So, in general, you'll still end up with a super extremal black hole if you really had thermal photons being. But of course, it's no longer clear that the radiation is thermal because that came out of this semi-classical calculation, which we now don't think is good. So what we really should be doing is taking the same strategy that Luca and Joaquim did to study the thermodynamics, but now use it to study the dynamics of the black hole and what sort of particles can emit. So actually calculate the radiation spectrum from the black hole. So that's the goal of this paper, and it's taken us about 4 years to do it, but we're now pretty happy. We've been happy at various stages before and then realized we were doing stuff totally wrong. So, who knows what will change in the future. But as of now, I claim we know all the answers.
Just a quick
Yep.
question. So, for a black hole formed from collapsed radiation was never actually thermal to begin with.
Very, very close to it.
Well, I mean, it's purifying with time, so it's not actually.
So you mean because of the page time? Yeah, I mean, this will generally happen well before the page time, but that was also why I said the thing about the information problem and the takeaway being that if you only care about the energy spectrum and stuff, then
Right, so that's all you're going to care about in this.
yeah,
Okay.
I'm not interested in information being preserved or anything fancy like that. Just, what sort of particles, if you're at infinity and just looking at what stuff is coming out of the black hole, what are you going to see?
You look at
Basic
local
observations.
stuff.
Yeah, just.
So the Unruh approximation that gives you the thermal.
Yes, that relied on having a classical
Classical.
geometry, so we don't know it's true. Okay, so I made a big deal about how this talk is going to be about our universe, but for 2 slides, we're going to forget about that and do something a bit simpler. We're going to imagine we had a massless scalar field, and we're going to ask what would that massless scalar field do? Okay, so of course we don't. The only scalar fields we know about in our universe, the Higgs, it's massive. But let's say we had a massless one. How would we calculate how it radiates? So let's first talk about how Hawking calculated how it radiates, because this is the first calculation Hawking did. So consider the scalar field. And I already told you that the Unruh effect tells us that very close to the horizon, we have thermal modes that look exactly thermal. And then I said some vague words about, those modes are able to go out to infinity. But that's not necessarily what they actually do, right? Because what you actually have to do is solve the full dynamics in the GR background, scalar field in the black hole background. But when you do that, what you find is that the problem basically reduces to a one-dimensional scattering problem with some effective potential. So you just solve the scalar field wave equation in the curved spacetime, rewrite it, and you get it looking like this. You can see my laser pointer. It has some effective potential that vanishes very close to the horizon, also vanishes at it where it's thermal, it vanishes at infinity where it's free streaming modes, but then there's some scattering. These give what's called gray body factors.
Thanks for stealing
In
my.
general, you have to just compute these things numerically, like for a Schwarzschild black hole, there's no analytic solution to what these are. But it turns out actually for near extremal black holes, you can do better and you can analytically solve them. Basically, the way you do it is you split the problem up into 3 overlapping regions. Very close to the horizon, you basically have anti-de Sitter space. Turns out it's solvable there. In the middle, the energy of these photons is going to be very, very small. So you can basically, the effective potential is large. So you can basically ignore the energy of the photons. That is also solvable. And then finally, very far away from the black hole, you basically just have photons experiencing a centrifugal force. And again, that's solvable. So you can overlap the different solutions, match them together and get an analytic solution that says the probability of a thermal photon near the horizon making out to infinity scales as the energy squared in times the horizon's radius of the black hole spot. Okay, so that becomes very small as the black hole gets cold because the energy of the photon gets small. Yeah.
If your black hole is non-extremal and instead of having ADS2, you have Rindler, can't you also like exactly solve and then use that analytically?
No. So it just turns out that basically because omega, this approximation where omega equals 0 only works because the temperature of the black hole is so low. It's because there's been this huge amount of redshifting already before you get out of the ADS2 region. Rindler doesn't have redshifting, so yeah. Okay, so the evaporation of these things is actually slower than you might think, even for how small the temperature is getting, because the thermal photons almost all the time just get reflected back into the black hole. It's only occasionally that they're actually going to escape all the way out. This turns out to be very helpful for us, because we want to try to give a fully quantum description of these almost zero modes. And the way we're going to do that, so in the near horizon region, that looks like ADS2, then we can give a completely quantum description where it has 3 things. It has JT gravity, it has this SU2 gauge theory that describes the rotations of the black hole, and it has our matter scalar field.
Is the location of that peak in the limit that you're in such a very
Yeah.
near extremality? Wouldn't it be moving?
No. The ADS2 region is sort of in the tail of this effective potential. The peak is like 2R plus or whatever. 1.5R plus, something like that.
But it's
Even
location
if-
relative to the horizon.
Oh, yes, of course. But we don't really care about where the horizon is, right? Like if I go back here, so I mean the horizon's off at infinity in tortoise coordinates anyway. But it's only in tortoise coordinates, it's only very far over to the left where the temperature of the black hole matters. And that's
But its proper distance would be a function of,
yes.
wouldn't it? I thought the distance was infinite when m is equal to q, the proper
This
distance.
V will depend on the temperature of the black hole very far over here, and that will affect the gray body factors. And so in general, yes, the gray body factors will depend on the temperature of the black hole, but only from this sort of ADS2 piece. This piece and this piece don't care about the temperature of the black hole.
I see.
Yeah. Okay. Great.
But somehow if the temperature is 0, nothing should be happening.
Yeah. So this is all true in the limit where the temperature is very well. If the temperature is 0, but omega is finite, if you just had some actual scattering problem, maybe you have some ingoing
I see.
particle or something, then you can still ask about the gray body factor even at 0 temperature.
Sir, can I ask
Yes.
a very stupid question? So how is this different to how people compute a quasi-normal mode frequency for black holes? In the sense that what's your F that you've chosen? If I look at that formula, it looks very familiar.
Yeah. It is. I mean, quasi-normal modes. You're solving for imaginary frequency solutions. They're exponential, but this is just the same scattering problem that would appear in the quasi-normal mode problem. Yeah, this is just the same. Yeah, it's the physics of things scattering off the black hole. It's nothing. This is going to be very different, what I'm about to do now. So we have this near horizon region, and we're going to give it a completely quantum description where we sort of fully quantize, not just perturbatively, but fully quantize these almost zero modes. That's solvable. I'm not going to explain how it's solvable, but experts in the room will know. Separately, we have degrees of freedom sort of far away from the black hole. The only sort of quantum ones are just fluctuations of the scalar field in this fixed background, the only ones we're caring about now. Again, that's a totally solvable free quantum theory. So both of these things are fine. And the important point is because the gray body factor is really, really small when we've gone to cold temperatures, then at leading order, these two regions are just totally decoupled. So the combined system is also solvable in the approximation where they're not coupled at all. Now, of course, they really are coupled. That's how you have any non-zero gray body factor at all. But you can treat that coupling between the two regions perturbed. It is actually really, really tiny. It's like 10 to the minus 100 or something for practical purposes. And the way that the perturbative interaction you get is well understood from things like ADS, CFT, and so on. But you can just derive it completely in gravity. And what it is that the far field modes reflecting off the black hole act as a source for the scalar field modes in the near horizon region. They sort of change the boundary conditions of the near horizon region, and that changes the physics in a way that's understood. And so you can write down some interaction Hamiltonian between this sort of fully quantum treatment of the near horizon region and the semi-classical treatment of the stuff far away from the black hole. And basically it's some Hamiltonian that is a product of some sort of matter operator in this near horizon theory, and sum of creation and annihilation operators for the scalar field far away from the black. Okay, this is just comes from working things out. Okay, great. So then we now have two systems that are perturbatively coupled together, and we want to know how that perturbative coupling causes transitions between different states of those systems. Again, this is a very well understood problem in an undergraduate quantum mechanics course. You'll do this. The way you do it uses what's called Fermi's golden rule. So this just follows from doing perturbative quantum mechanics. You get some formula that looks like a matrix element squared for this interaction Hamiltonian times a delta function. There's some typos in there, but never mind. So it ends up reducing to a 2-point function in this near horizon region, which is basically just JT gravity in this case. That 2-point function is known exactly. So you can just plug in that formula and you get some transition rate. And what you find is that if the energy of the black hole above extremality, I call that EI, is well above this scale where we started running into problems, then the sort of fully quantum formula basically looks like the semi-classical formula. Hawking radiation still looks basically like what you expect. But if you go to really, really low energies above extremality, where seemingly you got nonsense, then you don't get anything that looks like the semi-classical answer. Instead, you get some nice curve for the energy of the photon that gets emitted. There's this orange curve. And in particular, you see it nicely drops down and goes to 0 at EI. That's saying that there's no way to emit a photon with energy more than the energy of the black hole above extremality. So you never get any problems with naked singularities, super extremal black holes, just everything gives sensible answers. Okay, so that's great, except of course we have no massless scalar fields in our universe. That's good because it's going to get more fun when we get to photons. So what happens when you have photons? Well, things get messier and more complicated. So even semi-classically, that's true. So the massless scalar fields in our universe are two things. Firstly, we have photons, which have spin 1, and secondly, we have gravitons that have spin 2. So very naively, and I forget how long we thought this was true because we hadn't read the literature well enough, but very naively, you might think that when you get to low temperatures and low energies, then photon emissions should dominate. And the reason for this is that far from the black hole, the effective potential is basically just a centrifugal potential that grows with the angular momentum. And so the less angular momentum you have, the easier it is to sort of tunnel through that centrifugal barrier. So this would be true if photons were just some random vector field sitting around the black hole. But they're not. They're the same vector field that the black hole is very highly charged under. That changes the perturbative dynamics, the fluctuations, and you get something called photon-graviton mixing, where in the near horizon region, the sort of relevant set of modes are superpositions of metric and electromagnetic fluctuations. Turns out that the sort of lightest mode in the near horizon region, the mode what's called the smallest scaling dimension, is actually an angular momentum 2 mode that's a particular mixture of the photon and the graviton, called graviphoton. So when this escapes out to infinity, it becomes a superposition of the photon. The graviton, and because that's the lightest mode near the horizon, that sort of cancels out, that it has less suppression there, and that cancels out the extra suppression it has far away from the horizon. And it turns out that in the end, semi-classically, this contributes roughly the same amount of radiation that the L equals 1 photon mode does, even at very low temperatures. Okay, so you have some combination of these two things. So just like for the massless scalar field, we can go through the same rigmarole of doing all of this not semi-classically but fully quantum mechanically. We just have to do the near horizon region as basically 2D scalar fields of different masses. The far horizon region has these photons and gravitons scattering off stuff. We have an interaction. Go through it all, and again, here are some nice curves showing that at high temperatures it looks semi-classical, and at low temperatures it starts to look very different. But I'm not going to talk about that too much, because something much more fun happens. It took us over 3 years to notice that it's actually pretty obvious. And that's that the extremality bound says that a black hole with angular momentum J has to have mass not just equal to Q, but Q plus something that's order J squared, right? In fact, quantum mechanically, J squared becomes J plus 1 for all the usual reasons it does. And the coefficient in front of it turns out to be exactly the same breakdown scale that showed up before. So if the black hole has sort of angular momentum 1 in units of h bar, then the mass needs to be at least Q plus E breakdown. Okay, that's fine. But angular momentum is conserved. Okay, in our theory, it's conserved in the near horizon, it's conserved far horizon, it's conserved by perturbative interaction. And angular momentum selection rules say that if we start the black hole with angular momentum 0, we emit a photon with angular momentum 1, then our black hole must now also have angular momentum 1. Okay, great. But now let's say we start with a black hole with some energy here that's less than Q plus E breakdown. It wants to emit a photon and go to some lower energy state with angular momentum 1. But as you can see from my nice little figure, there are no such states. So it is, in fact, not possible at all for a sufficiently cold near extremal black hole to emit a photon or a graviton. It can't happen. Okay. So this is, again, something that's very familiar from undergraduate quantum mechanics. Something that just shows up in atomic physics. It's called a forbidden transition. The classic example is if you have a hydrogen atom with the electron in the 2s orbital, it wants to drop down to the 1s, but it can't emit a single photon to do that, and so it's said to be forbidden. And forbidden transitions can happen. In quantum mechanics, pretty much anything can happen, but they're incredibly slow. So in the hydrogen atom, the lifetime of the 2p orbital is order a nanosecond. It can just emit a photon and drop down. The 2s orbital has a lifetime that's close to a second. So it's incredibly slow. And that's in a perturbative expansion where the perturbative parameter is alpha, so it's about 1 over 137. We're going to be dealing with perturbative expansions where the parameter is like 10 to the minus 100. So things are going to get really slow when we get down to these temperatures and we can't emit a single photon anymore. But what does happen? Well, you can't emit a single photon because you can't conserve angular momentum, so instead you emit 2 photons. You have 2 photons, they can be in an entangled state where they have total angular momentum 0. And so the black hole can remain in a state with angular momentum 0. So in between emitting these 2 photons, the black hole is sort of said to be off shell. It's not in a on-shell state. But this just comes from doing perturbation theory in quantum mechanics. All you have to do is do the same derivation that gave you Fermi-Jordan rule, but go to one higher order in perturbation theory first. And you get something that you probably haven't ever seen before, but should look pretty familiar from an undergraduate quantum mechanics course. You have some 1 over the difference between the on-shell and off-shell energies, summing over intermediate off-shell intermediate states. You have 2 factors of the interaction Hamiltonian, so on. Okay, great. This thing then just reduces to a 4-point function in JT gravity. That's a bit horrible, but it's known. It's just, people have done the calculations. We don't need to. It involves this nasty little thing here that I'm not even going to define. It's called a 6J symbol. Never mind. We have some horrible, disgusting 3-line formula. But all we really care about is sort of how things scale with energy as we get really close to extremality. And in that limit, a lot of this just reduces to constant things that you can numerically integrate over in Mathematica. And you end up with some constant that turns out to be about 10 to the minus 4 times the energy of the black hole above extremality to the power of 17 over 2. So this is a much higher power than we had before. Things are getting incredibly slow. But eventually the black hole does get colder.
This bound E greater
Don't we
than.
have, here, you can put that
That's
there.
just the temperature
Don't we have
formula.
one
That's just the standard.
of those cocktails left?
If it
She
was
didn't
J
have more
squared
left.
rather than JJ plus
She
1, it would just be the usual extremality. bound
Yeah,
for
we have
black
one
holes
left. I
in
was
the
gonna
limit
get her
where J
the,
is small.
the,
The JJ plus 1 instead comes from, you need to quantize
old-fashioned
the
in Manhattan.
rotational fluctuations.
what did you have,
and you
what did we
just
have
end
last
up-
time?
It ends up becoming just some like SU2 rigid rotor.
Manhattan.
Yeah, it was
The high
Manhattan.
energies is classical and you get the J squared.
Which she really likes.
That self doesn't break down here.
Okay, I just
So, I mean,
figured
we're,
we don't need
you
to
know,
buy two.
it does,
No,
right? It
no,
goes
we'll
from
buy
J
one.
squared to JJ plus 1. But we're just treating the fluctuations in the relevant modes completely.
And one is enough for
and-
3
and-
drinks.
Yeah. Of course, you could worry that there's something else we're missing, but
Pardon?
this
One is enough for 3 servings.
Right.
the principled treatment, given everything we understand about quantum gravity, and it seems to give completely sensible answers. Yeah. Like, so we there are almost 0 modes where the black hole is just very slowly rotating, right? Where basically you go from the near extremal black hole to the near extremal black hole with a bit of angular momentum. And you can just quantize those modes and they just give you a.
But in that window there, the spacing between microstates, you would expect to be exponentially
Yes,
small.
yes.
And each of those microstates would be an angular momentum eigenstate, right?
Yes, yes.
So why is
So
there
if we
all
go,
kinds of
yeah, let me go back here. So this is like the sort of density of states you get from this sort of fully quantum treatment, right? So yeah, really there's an exponential density of states here, but within this approximation, it's basically continuous. But yeah, within each angular momentum sector, you get like only discrete values of the angular momentum allowed, half integer and integer ones, and the density of states starts at J plus 1 over 2e breakdown.
Wait, so you're saying that those. Are you saying that the states in that band, the lowest band there, which are only exponentially, with exponentially small separations, all have 0 angles?
Yes. This is all states with exactly 0 angular momentum. And then the states with angular momentum of half start here and start higher and so on.
If those are all 0 angle momentum, that sounds so surprising, doesn't it?
Doesn't it?
Wouldn't you?
I don't know. There's like a BPS in like, it's not BPS bound, but there's like some bound that says, right, like, what would you expect? You'd expect them
Well,
to
if you take, say, some stringy model where you have something at extremality.
Yeah.
With 0 angular momentum.
Yeah.
Microstates in there will typically all carry very large angular momentum.
Yeah.
And then if you perturb that by adding something that breaks supersymmetry or something, so that changing your dynamics in a way that this breaks supersymmetry, all those states get separated.
Yeah.
To exponentially small spacings with one lowest energy.
So the exact degeneracy of states in like a supersymmetric black hole in string theory, all the states in that degeneracy have exactly 0 angular momentum, right? Because otherwise they'd violate the BPS bound. Or like
There's H bars in there.
maybe in the free.
Oh, they're made out of fermion. They're made out of the, fermion going around the string. All
Yeah,
that's
let's talk about this offline, I think, but yeah. Let's talk about it offline. Okay.
Sorry, Jeff, this is a JT, you're essentially doing the JT calculation here?
Yes.
Can you reproduce this from the matrix model?
I mean, you could, yes. I mean, it's matrix, like, we're not doing anything involving high topologies right now, so that's fancier than we need, but yeah. It will come from bulk JT, it would come from matrix model, it would, yeah. Okay, great. Okay, so how tight is the?
It's quite tight.
Okay, let me go fast through this, because this is actually quite boring. And you can apologize to Andy can apologize for me having to go fast through it. Okay, so we also have to worry about charged particle emission, of course. Basically, the way charged particle emission works is you have some effective potential for the charged particle that goes up a little bit and then it goes down. It goes up because very near the horizon, everything's going to fall across the horizon. It then goes down because the electrostatic repulsion is stronger than gravitational attraction. Okay. So inside this barrier, you have thermal Hawking electrons. There's some little barrier. The swing effect comes from the probability that a thermal electron has enough energy to get over that barrier. And then once it's over the barrier, it just gets shot off to infinity very, very fast. Okay. So in particular, there's an important point here, which is that naively, you think after emitting the electron, the mass of the black hole will be its original mass minus the mass of the electron, charge the original charge minus charge of the electron. That's not actually true, because once it gets over this barrier, the electron gets accelerated to an ultra-relativistic velocity. And in fact, by the time it reaches infinity, it has nearly Planckian energy. The black hole stays pretty close to extremality, but if you go like higher order corrections, you'll realize that it's not actually extremal. It does actually get quite a lot hotter. In particular, it gets well above E breakdown. The black hole will become classical. Of course, that's all semi-classically. You might, since there are such big corrections for neutral particles, you might also expect there to be similar ones for charged particles. So you can do a very fancy and involved calculation. So there's some semi-classical instanton that describes the swing effect. You can include gravitational back reaction in that instanton. And the effect of the back reaction is that the sort of solution has this effective conical deficit from the fact that basically the periodicity of the black hole inside the electron world line is different from the periodicity outside. So from the outside point of view, you have a conical deficit. And then you can take multi-instanton solutions with a load of conical deficits, and you can integrate over metric fluctuations about those solutions. So that's a problem. It's again a problem that has been well studied. After a very complicated calculation, you find some nice answer where summing over some instantons gives you some sort of exponential decay rate, some signature of a constant emission rate. Exponentially decays as a function of Euclidean time, the function of time. And you go, does this match the semi-classical answer? We did the calculation and it didn't. It changed by some polynomial factor, and we were like, oh, that's really cool. And then at some point, a year or two later, we realized we'd done the semi-classical calculation slightly wrong because we missed gravitational time dilation. And then we'd also made a subtle error with the normalization of this thing and various other stuff. And after 3 and a bit years or whatever, you end up realizing that it's exactly equal to the semi-classical answer after exponentially small correction. So sometimes things turn out to be interesting, sometimes they don't. But it turns out if you really put a lot of effort in, and trust me, we did, you conclude that the semi-classical answer is totally fine. Okay, great. So we're now almost done, which is good. So the black hole remains near extremal, but when it emits a charged particle, it gets a lot hotter again. So it got really, really cold probably because that was an exponentially slow process, but it eventually happened. It's now hot again. It again starts doing semi-classical radiation. Everything seems exactly the same, except that it isn't. And the reason it isn't is that the electron is a fermion, and so it has spin 1/2. And so when the fermion gets emitted, if the black hole was previously at J = 0, it ends up having 1/2 integer spin. It will probably be some large 1/2 integer spin, but it will be 1/2 integer. Then it emits a load of photons and graviphotons, but those all carry integer spin. So it stays at half integer spin, whatever happens. And it's never able to get back to J equals 0. So rather than at low temperatures settling down at J equals 0 again, instead the lowest it can get is down to one of these states with J equals a half. Okay. But of course, selection rules say that if you start with J equals a half and you emit a photon with angular momentum 1, you can stay with J equals a half, right? It appears in the tensor product, there's nothing wrong with that. So this time the black hole is allowed to do single photon transition. So it's in a totally different phase based on whether it's fermionic or bosonic, and it sort of switches between them every time it emits an electron after exponentially long periods. So the cooling rate is vastly faster. Okay, great. So we now have everything we need to tell the complete story of some generic, very large black hole. Initially, we get just semi-classical radiation, photons and graviphotons. It gets colder and colder and colder. Eventually, it gets down to this breakdown scale where we would have just said we have no clue what's going on from here on previously. But now we know that what happens is it gets driven down towards J equals 0, and then the evaporation rate slows down dramatically because it can now suddenly only emit pairs of photons. It does so in a very non-thermal quantum way, but it does so. It does so for an exponentially long time. Then suddenly, positron or electron will get emitted, and we'll jump back up to some comparatively high temperature. Then we're back to semi-classical radiation again, till it gets down to the breakdown scale. But now at the breakdown scale, it gets J equals a half and goes to just highly quantum photon emission. That's again non-thermal, but we still have single photon emission. And then eventually it will emit another electron, and we're back to step 1. It goes through the cycle again. After enough cycles, after enough times, cooling slowly down, then emitting an electron and jumping to a much smaller mass and one smaller time, then cooling down to the exponentially long time again. Eventually, the charge reaches 10 to the 44 or so, and the Schwinger effect stops being exponentially suppressed. The long wait times get shorter and shorter. It starts to go further away from extremality. From this point, basically what happens is the charge of the black hole will scale with the mass such that the electric field at the horizon stays roughly at the critical value for the Schwinger effect. This keeps the electron emission rate roughly comparable with the neutral radiation, so that it sort of stays, there's this like critical equilibrium that it will stay close to. So we'll get pretty quickly to something that looks like Schwarzschild while still being pretty big. Then we lose more mass. Eventually we get down to a handful of Planck masses. Again, we lose total control. We don't know any more about that than we did. But we've now, for these very large black holes, got to the state where we have as much control as we did for sort of normal sized black holes. Okay, cool. So I'm basically out of time. So let me just show. I'm not really sure what we learned from this, but here are some possibilities. Yeah, that's all I have. So thanks very much for asking me to talk.
If there's one or two pressing questions that we can, or if everyone's remembering them.
I would.
Actually, maybe I have a question, if that's all right.
Yep.
Sorry, people. So the 2-point functions that go into the and 4-point functions that go into these computations, they're the JT ones, or are they?
Yeah, they're basically, I mean, the JT plus some other stuff.
Sure,
So you
right.
have like angular momentum factors that,
Right.
you know, but the sort of the interesting part is JT plus mounted 2-point functions.
I'll ask you some more about that.
Yep.
Can I ask a follow-up to that? Sorry. So I lost track a little bit of what is exponential timescales here and what isn't. But
Yep.
I'm not asking you to clarify all of the timescales at this point, but if you're using 2-point functions in JT, at some point, if you wait long enough, you can have more about recurrences.
Yeah, we're not getting to that scale. There's no e to the s's involved.
Because when you
Well,
say
that-
exponentially long timescales,
Yes.
what is it?
Yes, I mean e to the charge divided by this critical charge, 10 to the 44. So in particular, if you made the charge really, really big, like 10 to the 100 or whatever, then the charge still only scales like the square root of the entropy. So this is e to the square root s, but also with this 10 to the minus 44 prefactor, so it's really very short compared to square root s. Yeah.
Okay, let's think of it again.